Now we're going to look at evaluating limits at infinity using algebraic means rather than just looking at a graph or typing in large values into a table. And I'm going to start by looking at a theorem. So for all values of n greater than 0, where n is some integer value or a fixed value, we see that the limit as x approaches infinity of x to the n is equal to infinity. And this is something that looks like complicated notation, and really it's something that you already know. So we looked at an example where n equals 2, and we saw um, when you look at x squared, if I let x go to infinity of the function x squared, we know that that's, well, bigger and bigger values. As x goes to infinity, squaring that infinite value will also go to infinity, and we end up getting bigger and bigger and bigger. So we saw before that the limit as x approaches infinity of some sort of polynomial x squared, that's just going to approach infinity. And sort of conversely, we see that as x goes to infinity of 1 over x to the n, that function is going to go to 0. And the example that we looked at previously was the limit as x approaches infinity of the function 1 over x. So in this case, our n was just 1. But you would think that if you had bigger and bigger values on this exponent, that would just be 1 over infinity, and 1 over infinity will get smaller and smaller and smaller. It's just a smaller and smaller fraction. That if I plug in a million, this gives me out 1 millionth. So this goes to 0. These tools are going to be helpful in evaluating limits algebraically. Let's return to one of the examples that we looked at when we were evaluating them graphically and numerically in GeoGebra. So this is the function k of x, which is equal to 2x squared plus 3x minus 1, all divided by 3x squared minus 5x plus 4. So this is a rational function. It's a rational function because I have a ratio of two different polynomials. And before we estimated that we thought the end behavior, or the limit at infinity, was going to be 2/3. Let's verify that formally. And we're going to verify that by doing a clever trick. I'm going to multiply top and bottom by a clever version of 1. And I'm going to multiply top and bottom both by 1 over x squared. And why am I choosing 1 over x squared? Well, we'll see in a second that it gives us something nice. But I'm choosing x squared because 2 is the largest degree of either of the top or the bottom polynomial. So when I multiply top and bottom by 1 over x squared, what result do I get out? I'm not changing this function at all. I'm just rewriting it in a different form. I'm going to use the distributive property here because I'm multiplying this single term, or this single factor, by each of these terms. So the first step of multiplication in the numerator is going to be 2x squared times 1 over x squared. And I'm going to write this out longhand for the first example so that it's very clear what the multiplication is that's going on. Next, I'm going to multiply 3x by 1 over x squared. And finally, I'm going to multiply negative 1 by 1 over x squared. And I'm going to do the same thing in the denominator. In the denominator, I get 3x squared times 1 over x squared plus, or minus 5x times 1 over x squared plus 4 times 1 over x squared. Now let's do this multiplication and simplify. The 2x squared divided by x squared, these x squareds are going to cancel each other out, and I'm left with just 2. Next, over here, I have 3x divided by x squared. One of these x's canceled with one of the x's in the x squared, and I'm left with an x in the denominator. So that leaves me with the term 3 divided by x. And the final term here, I have 1 times 1 over x squared. That's just going to be 1 over x squared. So I subtract 1 over x squared. That's my numerator. Let's take a look at the denominator. Similarly, 3x squared divided by x squared is going to leave me with 3. Negative 5x divided by x squared leaves me with negative 5 over x, and 4 divided by x squared gives me plus 4 over x squared. So what did I do to my function? This is the same function as we had before. I'm just writing it in a slightly different way. And what happens when I write it in this way? Well, now let's consider the limit as x approaches infinity of this new function, the new function given by 2 plus 3 over x minus 1 over x squared, all divided by 3 minus 5x plus 4 over x squared. Notice, by one of our previous theorems that we saw, we know that things like 1 over x and 1 over x squared and 1 over x cubed, all of these terms are going to go to 0 as I take this limit, because the denominator in each of these terms is shooting off towards infinity, whereas the numerator is just being held at some fixed number. And 5 divided by 1,000,000 is going to be a really, really small value. So we see that this limit becomes 2/3, which is exactly the limit that we anticipated that it was going to be. And now we've verified it algebraically. Let's look at one more example, and then we can generalize our results of these examples. So this is an example of another rational function. This time we're going to look at the rational function L of x is equal to 5x cubed minus 3x plus 2 divided by 2x squared minus x minus 1. And you might anticipate that our limit is going to end up being 5/2 when we let our x's go to infinity. But let's see whether or not that's the case. I'm going to multiply both top and bottom by something, and I want to make sure that I get rid of every single one of these x values. So I'm going to multiply, and I'll write this to the side. Multiply by 1 over x to the n divided by 1 over x to the n. And what is the n that I want? Where n is the largest power, and we would say that it's actually the largest degree. Oh, that got really blurry for a second. So in this case, I have an x cubed on top and an x squared on bottom. I'm going to multiply both top and bottom by 1 over x cubed, because I want to get rid of that x cubed. And I know it'll cancel out the x squared, so I get to the other lower terms. So I'm multiplying both top and bottom by 1 over x cubed. Why can't I multiply the top by 1 over x cubed and the bottom by 1 over x squared? If I multiply the top and the bottom by two different numbers, then it won't be equivalent anymore, and I want to make sure that my function is exactly the same. So what happens when I do this multiplication? The x cubed and the x cubed cancel. I'm left with 5 minus one of this x cancels one of those x's, so I'm left with minus 3 divided by x squared, and then plus 2 divided by x cubed. That's what the numerator looks like. Let's look at the denominator. Here I have 2x squared divided by x cubed, so 2 of the x's will cancel, and I'm left with 2 divided by x, because one of the x's is left over. And then I subtract x divided by x cubed. One of those x's will cancel, and I'm left with 1 over x squared, and then minus 1 over x cubed. So that's what our function looks like as I rewrite it. Let's consider the limit of L of x as my x approaches infinity. And in this case, we see that all of these terms are going to go to 0. They're going to 0 because my numerator is just a single value and my denominator is shooting off to infinity. And so I'm left with 5 over 0. And 5 is a single number, and 0 is infinitely small. And thus, this limit is going to approach infinity. Because this is the same question as asking how many children, if I have 5 jelly beans and I give each child 0 jelly beans, how many children can I give jelly beans to? Well, I'm giving it to an infinite number of children because every time I give a child 0 jelly beans, I'll always have 5 remaining. So this is our indeterminate, well, it's not an indeterminate form, pardon me. This is our form where it shoots off to infinity. From these two examples, we can generalize our result. We can see that if the top polynomial and the bottom polynomial have the same degree, it really doesn't matter what all of the final terms are. Really, we're only interested in comparing the leading terms. And if the leading terms are both the same degree, so I'll give an example of that. If my leading terms look something like x to the n divided by x to the n, maybe I'll say kx to the n divided by Lx to the n, where these are my coefficients, we know that the limit as x approaches infinity of this function, everything else is going to cancel, and the x to n's cancel, and I'm left with my k over L as my limit result. However, if I have a function f of x where m is greater than n, and it's a function kx to the m divided by Lx to the n, as we just saw, if the numerator is really big, we're going to get the limit as x approaches infinity of my function f of x. It's not going to matter that this small term has an L in front of it. It's still going to be too small to compete with this greater power, and it's going to give me something like k over 0, which is approaching an infinite result.